Hello students. So today we will be seeing some practical examples first, then followed by week 12 content. So I'll just start with some of the practical examples. Please stay tuned using MATLAB. So you can see here, this script generates a healthy fan signal that you will use in this module. Remember, because here we are doing this estimating the power spectral density, because I got questions from Manisha how to do this power spectral density and she is having some doubts. So she was the only student, so I'm just taking all those things. First, first I'll clear the doubts, then I will go to week 12 content. Okay. In the week 12, actually, there's a relay fading and different type of fading techniques are there for the wireless communication. So if we can define this sample rate in time vectors, this is a sample rate time vector as we can do and create a variable for the fan rotation speed, that is Fr is equals to 4000 divided 60, and it will create a signal with the fundamental frequency and two harmonics, vary the amplitude based on the real time data. So how it is created, you can see why two harmonics, because here 2 pi fr into t and here 3 fr. Okay, so fr and the 3 fr are the two harmonics. Okay, and 4 fr. So these are the fr, and it will create a signal with two harmonics. Why? How can you see the two harmonics? Two harmonics with the two frequencies. Okay, and it will vary the amplitude based on the real world data. So I don't know whether my screen is shared or not. Please, Manisha, verify. So Fourier transform. So in the previous modules, we have seen that power spectral function used to estimate the frequency content of our signal or your signal. The PS spectrum function as well as other MATLAB functions for analyzing signals in the frequency domain like periodogram and the Welch use the Fourier transform. Okay. So in this lesson, you will learn about the Fourier transform so that you can tailor the techniques to get more accurate results for the different types of signals. So these are the discrete time Fourier transform. So here we are having, you can see here and analyze it, discrete Fourier transform. So time domain you have uh, 0 to 1 like that, and dt is 1 upon fs, and so x is a vector of length x, small x, and the samples are equally spaced by 1 by fs. So let's see this FFT functions. In this activity, you will use FFT to calculate the spectrum of the fan vibration signal. Use the FFT function to estimate the frequencies in signal. So how can you do? So we have to name signal name is SIG. It's already there. So these are the workspace that is already there, FR, FSM, and signal and T. So what you have to do, we have to output Y is supposed. We have to see actually how this FFT and FR spectral density looks like. So that's why I'm giving a practical example. That's because this course was all about the MATLAB. So let's do this FFT, then SIG. Okay. So see, you can see the signal Y is FFT of that. Store the length of the signal in the variable name. So I'm just keeping n is equals to length y. Okay. Sorry, not FFT. You're asking about signal. So like that, by small steps only, we'll understand. To visualize a Fourier transform, you need to calculate the Fourier frequency points per f for your FFT vector. So this is similar to calculating the time vector. So let's first calculate. So create a function vector f that contains a frequency for the each element in y. So let's zero, because anyway it will go to uh, 0 to n minus 1, because that is a this is a length of the vector, and then we have to multiply by fs by n. Why fs? Fs is the signal frequency. So these are the things. Y contains a complex number. To visualize the magnitude of each of frequency, you can calculate the absolute value before you plot the spectrum. Usually the power spectrum is displayed. The units of the power spectrum are the squared magnitude or the frequency domain representation. So first of all, let's save the squared. So I'm just keeping apps squared SQRT. I can keep. Huh? Apps by now plot P. This is F, x-axis, and this is P. It will be correct. So you can see speak correct. I'm just squared out to okay. Square, I guess. Square. But I can just do this. Mm, Squared absolute value. Uh, I'll just see the solution. I think Manisha, can you please tell? Yeah, so dot power, it's not like that. Python, I was doing the Python. So dot power 2. Since each element we have to do, right? So here you can see the peaks at different frequencies. So this is a power spectrum, not power spectral density. It's a Fourier transform. This signal has a three dominant frequency. You can see here, which is repeating here. 1, 2, 3. Then here 1, 2, 3. A positive side and negative side. There are 6 peaks in the plot. So FFT returns the two-sided spectrum, and which you'll learn more later in the class. Because I told you when I was giving you example of modulation, how the cost modulation is giving to one here and then one here. What was one when I was talking about? That is a impulse function. That is an impulse. One here, one here. To plot the spectrum in the decibel, you can use 10 log 10p, where p is the power spectrum. So decibel, let's plot that. Why decibel we are talking about? Because uh, power is generally measured in the form of decibels. So you can see the how power spectral density is changing. So what it is showing actually, uh, here the power spectral is minus 60 dB, which is equivalent to somewhat log 10. You can keep minus 0.0001 value in the linear scale. And here you are having, wherever the peak is having, you are having the high power or the less power. So actually the negative scale is there. So if minus 20 is good, then is not is good, then minus 60. Okay, better than minus. The signal has three stones at the FR, 3 FR, 4 FR. The value of FR in the workspace FR, you can see here, 2400. In the plots, check the frequency locations are close to the correct location. If you'd like to learn more about Fourier transform, you can download the Fourier analysis module here. So let's do Fourier analysis module. Manisha, you are the only student here, so can you please say anything if something is missing or like that? So this is just my thing. Like, so let's read. This is very good. In generating signals and common signal operation module, you saw that the spectrum of a discrete time signals repeat, as we know. The different frequency ranges show different portions of the spectrum. The slide show below shows an example of different frequency ranges. All three spectra are of the same signal, which has a sample rate of 30 Hz. Frequency range of FFT. 30 Hz means here you'll have 30, then sample, same signals are repeating. So you can see here. By default, the FFT function spectrum extends from 0 to Fs, which shows that both sides of the spectrum are on the Nyquist frequency. Because the spectrum of the discrete time signal repeats, the frequencies at 10 Hz and 20 Hz are both from the same tone. So that's great. 10 Hz and 20 Hz, same tone, same frequency, okay? So you can shift the zero frequency component to the center of the spectrum to make it a centered spectrum. You can change the frequencies from two-sided to centered using the FFT shift. So let's see how we can use FFT shift. FFT shift is very common when you do the analysis using MATLAB for signal processing and communication. So center the frequency spectrum stored in the variable P. Okay, so FFT shift. So we have done correctly. You also need to shift your frequency values to match. Okay. For even FFT sizes, you can subtract fs by 2 from the frequency values. How will you do? Waiting for you, Manisha. Manisha, any output? Manisha, you're not active. I don't know. Right? But you need to shift the frequency values to match. So for even equity size, you can subtract fs by 2 from the frequency values. F is equals to f minus fs by 2. F shift f. I can understand in this you might have doubt. 20 log 10 p shift. See, sorry, the power spectrum is there. It's just 10 log, right? 20 log is for normal signals. What is it? At least you can point out the mistakes. And it's, oh, this F shift. See, I was defining above and this like this mistake. This happens. For the real valued signal, the power spectrum is symmetric around zero. So you only need to plot the one-sided spectrum. Save the first half of the F and P to first half and E half. So how can you only plot one side? Any idea? So what can I do here is uh, F is equals to 0 to F shift by 2 minus 1. Okay. And P is equals to 0 to F of is F only, right? P half P apps. So must be P 0 to length. Yes, length of P by 2 minus 1. And this is, since this is vector, so I'm doing like that. Simple, simple logic. Then plot the power spectrum in dV. Oh, so plot F half P half. Length of F is showing something wrong. Let's see the solution. N by 2. Simple length is stored in N. Length of signal is stored in N. We don't need to do this very often, right? N is already stored. So why to keep N by 2? And again, this is a linear scale, so we'll do what we'll do. 10, sorry, 10 log 10. So n was already stored, so no need to calculate again, because length of f is different from the length of signal. It's currently pointed. Where am I? See? Not -1, just because MATLAB won't start with one in basis. Anyway, you can do -1, but here the solutions are just fix it. So that's why it's like this. See, the same thing I'm writing still. Maybe semicolon or some inbuilt solution are there. -1 also you can do because it will calculate till the correct half. Okay, so just we can leave linear log scale difference. I got to this doubt from Ashutosh. He didn't join today. So you may have noticed that the y-axis has changed throughout the course so far. Sometimes the y-axis has a linear scale, and sometimes it has a log scale. Depending on which scale makes it easier to see all the tones in the frequency domain. So we can see here linear scale and the log scale. We can compare the power of two different tones in linear scale, but the small tone at 30 Hz is not visible. So log scale is 10 log linear scale. It's a video, just
Imagine the spectrum of a perfect 10 hertz sine wave. Imagine the spectrum of a perfect 10 hertz sine wave. You're probably thinking of something like this. There's only power at 10 hertz.
yeah. So I was just telling that Y sine and cosines are used for the oscillators in the modulators and modulation because it is having a single tone as we can see here. So do you think that if it is a single frequency or the single tone, it will have the single frequency or the single tone that what we are referring. And this is the only reason like why square waves or the triangular waves are not used as a carrier wave in modulation and in various scenarios like frequent Fourier series in that where we wrote a periodic signal as the sum of sinusoid and cosinusoid. So we are dealing only with sinusoid and cosinusoids. So what do you think? Do it really have a single tone or the same power at the same single frequency? In this model, we will see that.
This is the spectrum of a signal with infinite length. But most likely, your computer
Yes. So they basically, when we plot the spectrum of an infinite length signal, that is sine and cosine, that we assume is of infinite signal, is infinite length. But in practice, we don't have a signal of finite length. In practice, we don't have signal of infinite length. We have signal of finite length. So here where the pictures comes in, the computation and all those things change, varies.
doesn't have the space to store an infinite signal. Your signal has to be truncated. Now there's power at many frequencies.
Now, in this particular thing that if we have truncated signal, in that case, you're having the power at different frequencies, not only a single frequencies.
You might notice a discrepancy in the prominent frequency. See, in this example, the peak isn't precisely at 10 Hz. This is because the x-axis only contains frequencies at specific points. Here, there's no point at exactly 10 Hz. So the peak will be
Frequencies at 10 hertz.
located at the closest available point.
So the peak will be located at the closest available point.
To get more values on the x-axis, you can use a technique called zero padding. Zero padding makes the entire spectrum look smoother.
So what
There's
we are
still
exactly doing,
significant power,
zero paddings are also taught in the class.
so the peak will be located at the closest available point. To get more values on the x-axis, you can use a technique called
To have more values at the x-axis, we are doing the zero
zero
padding.
padding. Zero padding makes the entire spectrum look smoother.
And it makes the entire spectrum look smoother in the sense that it will have more values at the x-axis and more values at the y-axis. And it will smooth out.
There's still significant power at 10 Hz. But what's this other power? This is often called the main lobe, and
So in practice, as we are telling that the computer can't store the infinite signal, so it will have a finite duration signal and it will store the power of finite duration, and it will also have the power at other frequencies. So the other frequencies are called side lobes, whereas the main frequency where the power is more, it's called the main lobe.
these are the side lobes. In general, you want as much power at 10 Hz as possible. So you want a small main lobe width and a small side lobe height.
You want more power to be at the main frequency, because in practice it's very easy to deal with the single frequency things. So you want more side lobe, main lobe width and less side lobe length.
On the frequency axis, each side lobe is spaced by the sample rate over the signal's length. These zero crossings also determine the main lobe width. If you increase the signal's length, you decrease the main lobe width and the height of distant side lobes. But if you're using pre-recorded data, you may not have much control over your signal's length. So what else can you do? Windowing can decrease the side lobe height.
So please understand the logic here, what it is telling.
Recorded data side lobes. But if you're using pre-recorded data, you decrease. If you increase the signal's length, you decrease the main lobe.
So whenever the signal length is increasing, you are decreasing the main lobe width and the height of.
Lobe width and the height of distant side lobes. But if you're using pre-recorded data, you may not have much control over your signal's length. So what else can you do?
So because we can't change the signal length and all, so what else we can do?
Windowing can decrease the side lobe height at the expense of the main lobe width.
Windowing decrease the height of the side lobe, but at the expense of main lobe width.
Fourier transforms, zero padding, and windowing are often used together to create a clean.
The Fourier transform is used to see the the signal in the frequency domain. It is used for the spectrum analyzing. Okay, when we do the zero padding to have to smooth out the signals. Okay, you will have more values at the x-axis and the y-axis both. So at the end, you want to decrease further the powers at the side lobes. So you are doing windowing. Okay, windowing also decreases the main lobe height, but it's fine. You can smooth out and you can see the only single frequency or the more power at the same single frequency.
Spectrum. The periodogram function in MATLAB is a convenient way to apply all three techniques.
So this periodogram in MATLAB does all those things. FFT, zero padding, and the windowing. Okay. So in FFT, you will require signal. For the windowing, you will require window. Okay. And the zero padding is by default inbuilt. Okay. And size of FFT is also required. That's great. So in this lesson, you will use the periodogram function to calculate the spectrum. You can also use the function without outputs and make the MATLAB to plot for you. So here P is the PSD estimate, power spectral density estimate. F is the frequencies. Periodogram is the name of the function, by default function or inbuilt function that is we are using. Signal is the input data. Window is the window vector, is the same size as signal. By default, it is same size, but you can change the different size also. And NFFT is the number of DFT points, and FS is a sample rate. It's how we learn. Okay, it's all about power spectral density. That's the last, I think. So before estimating the spectrum of a signal with a periodogram, you can choose the winnowing function. So winnowing is a technique to reduce the effects from the truncating your signal. Okay. So what we with the effects we got some side lobe powers that we don't want actually. At the same time, we can't store the infinite length signal. Okay. So you'll learn about choosing a window later in the module. For now, you'll use a rectangular window. And we saw this actually in the week 8, I guess, this rectangular window and what type of windows, the windowing techniques were there. Okay, a rectangular window is a vector of ones that the same length as your signal. That's what I was telling you. You can change the different lengths as well with the Hamming window, other type of window techniques. So if you use the ones function with the one input, it will create a square matrix. The window should be a vector. So use two inputs. Direct win is equals to ones, one and okay. So create a rectangular window named W. So here we are having these things. We can see the workspace, how many variables are loaded. So FR, FS, N and signal and the T is loaded based on this. So signal is this and N is the length of the signal. So let's create a W as opposed to once. Now this length is N. So now the next input to the periodogram is the number of DFT points. Okay. So basically, number of DFT points, what you will do, generally your number of DFT points should be at least the length of the signal. You can increase the number of DFT points to zero, to zero pad the signal. Okay, as we know, it's for zero padding, you need to increase the number of inputs and the x-axis. So you'll learn more about zero padding the next lesson. So create a variable NFT that is equals to, it's very easy. NFT is equals to n. We are keeping that is equals to n, but in general it is not. So that's why it is explicitly mentioned in one of the tasks. Use the periodogram function with signal W and that. Okay. What were the inputs here? You can just use this periodogram or let's P is equals to periodo period. Let's first do help. I am knowing and just did it. So if we have one as output, you will have just this X. Okay. And if nothing is there, let's see periodogram. So you can also write like that. Just checking whether we can write in that way or not. So it's fine. It's F. I'm not keeping any output argument. I'm not keeping any output argument. It's anyway, it is not written here, so just signal W and FFT. What are this? So what are the functions that periodograms does? It first calculate the FFT, then zero padding, and then finally windowing. Okay, all threes can be seen here. So you can see only a single tone you're having. Okay, at frequency of somewhat around 0.1 or less than that. You can also use the periodogram with default inputs. So if you will specify your sample rate, use this. You can use simple use empty brackets for windowing and number of safety points. So plot using default inputs. So we want to see actually what default values it takes. So it's good. Plot. Oh, this is color. So you can observe what is the default values it is taking. Output in my sorry. So it is different from what we expected. I was thinking that the same power spectral density we'll see. If you want the power spectral density estimate as a vector, you can request the outputs from the periodogram. Where P is the magnitude of the power spectrum density. That's what I was doing with the help command. F is the frequency location. So P is the magnitude. Once you have the vectors, you can use them to customize the plot for further processing. Calculate the periodogram W and NFFT. Okay, use two outputs, then plot the estimates in linear scale. Okay, F. What was the output? W and FFT. Is it correct, Manisha? And plot only F. I did the same. So see, I have written the exact same. So what happens actually, inbuilt commands are used. Just copy. The rest of model learn the guidelines on how to choose a number of DFT points in a method. So finding frequency spikes is also important. So this is the last thing that I am dealing in zero padding. Okay, I will go when I will go to the some content. The goal of spectrum analysis is often to accurately find the frequency content in a signal. So after frequency domain conversion or the FFT or Fourier transform, we want to know the frequency content. That's why we are doing that. So in this module, you will use the find peak function to locate the frequency spikes. Uh, so P and the LO, find peaks, signal location number of peaks, N s- short str descent. By default, find peaks return the peaks in the order in which they occur. To return the most prominent peak, you can set the peaks sorting to descending order. Okay, find the most prominent peak in the PWR. Use F as a location vector. Name of the peak and the location respectively. So we can use this. I think I need to provide this descending orders. So by default, they have used so many things. I thought we can use without that also, not a problem. The correct frequency in the signal is fan rotating frequency. So basically, we understood some part. Okay, so I'm just leaving these things. Um, I want to show. Okay, we understood this thing, signal generation. Digital filters were not covered in the class, so we are just moving that. I want to show you this wireless communication relay fading north, which was the content of week 12. I want to show you some important functions. So MATLAB simulation can make your wireless communications design faster. So I want to show you some channel modeling. Fading channel. So yes, I want to teach you this because this is the content from week 11 and week 12 some part. So using a communication tool, you can implement the fading channels. So fading is what? So if you have transmitter and if you have receiver, it is not going directly and it is subjected to some obstacles or some deflections happen. So that causes fading. So in that, we need to model that. Okay. Because if you want to estimate something, you need to have at the same time some model. Give me a second, I will have one. So I'll teach you relay and racing fading, okay? Relay and the racing fading channels are the most useful models of the real world phenomena in the wireless communications. This phenomena include multipath scattering event effects, time dispersers, the time dispersion, and Doppler shifts that arise from the relative motion between the transmitter and the receiver. So transmitter is transmitting in this direction, and receiver is also moving. So you don't generally have the direct communication, the line of sight communication. So if this leads to multipass scattering effects, this leads to time dispersion and the Doppler shifts. You remember three terms, okay? This section gives a brief overview of the fading channels and describe how to implement them in MATLAB. So this figure depicts the direct and the major reflected paths between the stationary radio transmitter and the moving receiver. Okay, so you have the shaded shapes represent the reflectors such as these buildings. Okay. Now, the major paths result in the arrival of delayed version of the signal at the receiver. In addition, the radio signal undergoes scattering in a local scale at each major part. So it will have the scattering at this part, this part, this part, this part. Okay, and this is a transmitter receiver. Such local scattering typically results from reflections of the objects near the mobile. So these irresolvable components combine in the receiver and cause a phenomenon known as multipath fading. Okay, irresolved, irsolvable components. You remember irsolvable components. Due to this phenomena, each major path behaves as a discrete fading path. So typically, the fading process is characterized by Rayleigh distribution for a non-line of sight path and Rayleigh distribution for a line of sight path. So Rayleigh is the line of sight path and Rayleigh for the non-line of sight. You remember because these were the questions from the assignments. Okay. And we will explain why this is there. Rayleigh distribution for line of sight. I'll explain you using mathematics. We'll see this difference as well. First of all, let's take it. The relative motion between a transmitter and the receiver causes the Doppler shift. What is Doppler shift? Frequency difference will happen relative to the actual arrival. So local scattering typically comes from many angles around the mobile. This scenario causes a range of Doppler shifts known as Doppler spectrum. Okay. When you have range of Doppler shift with different angles, it will call it Doppler spectrum. The maximum Doppler shift corresponds to the local scattering components. Okay, the maximum opposite corresponds to local scaling couples whose directions exactly opposes the trajectory of mobile. When we have the 180-degree difference, so it will have a maximum operation. The channel filter applies the path gains to the input signal. So here you have channel signal in and channel filter signal out. The path gains are computed using either the Gaussian filtered noise or the sum of sinusoid method based on the settings during the fading channel object. So my objective is to tell you how to use MATLAB for this type of channels, the wireless communication, because these two channels are often used to model the communication system. Okay, that's great. So these blocks, you have MATLAB. So in single input, single output, you can use POM dot relay channel. In multiple input, multiple output, you can use POM dot MIMO channel. So in Simulink, you can use CISO fading channel and MIMO fading channel. So you have Gaussian, filtered Gaussian noise, sum of sinusoids, average path gains, polyphase interpolation, linear interpolation, correlation, and Rayleigh effects. This is for the Rayleigh fading channel. So if you want to see this, I'll show you this MIMO. These are the syntax. The MIMO means multiple antennas will be at their transmitter, multiple antennas as a receiver. So MIMO channel system object filters an output signal through a multiple input, multiple output fading channel. This object models the Rayleigh and the Rayleigh and the Rayleigh fading. It all models both. We have to specify the object, the input argument. Manisha is still here. So to filter an output signal through a MIMO multipath fading channel, create first of all you have to create the com dot. This is a class which will create an object. So MIMO channel object, it sets its properties. So you can use all the member functions of the MIMO class. Okay. It will call the object with arguments if they were a function, if it were a function. To learn more about the system, how system works, you can use the system objects. So here, these are the syntax: MIMO channel, MIMO channel name value. So it will create a MIMO frequency selective or the frequency flat channel system object. So again, there's a frequency selective and frequency flat where the the range of frequency where the amplitude is almost constant. That will be the frequency selective or the frequency flat channels. Okay. So it will use this form.mimo channel. It sets the properties using one or more name value argument. For example, com.mimo channel sample rate sets this input signal of sample rate to 2. Okay, you can see here path delays, average path gains. So these are the inputs. Now you may wonder how can we specify the Rayleigh and the Rayleigh. So basically, this object models the Rayleigh and the Rayleigh fading and represent this partial correlation between the links using the knocker product. So this knocker product model, knocker, because that relation should be there. Because in MIMO you have both, not only single Rayleigh and the Rayleigh. So I'm giving you the knocker product. Knocker product of representations of symmetric groups. So sometimes known as this one is an operation of two matrices of because it shows a correlation. So it will show the correlation of form of matrix. So resulting in a block matrix. So it is a specialization of tensor product, which is denoted by the same symbol from vectors to matrices and gives a matrix of the tensor product linear map with respect to standard choice of basis. Knocker product is to be distinguished from the usual matrix multiplication, which is entirely different operation because Knocker product is also known as matrix direct product. Suppose you have this, what it is showing. A Knocker B product is A11B, A1 and B. So A11 will be multiplied with all the B1 B components. Send A1 to B, then all the B components like that. So here you can see one will be multiplied with all zero. So 0, 5, 6, 7 will be here. Then 3 will be multiplied with 0, 15, 18, 21 like that. So it's simple. Okay. So I want to show the Rayleigh and the Rayleigh fading channel distribution, how it looks like. So the wireless system consists of transmitter, receiver, and the channel. Basic thing. The channel between transmitter and the receiver can be time varying or the fixed. Okay. The fading refers to the variation in the received signal strength with respect to time due to channel seen by the transmitted signal over the path of the travel. Channel fading occurs due to various factors which include atmospheric and the physical. Rain, lightning, physical movement of transmitter receiver, path gain, path loss, parameters, etc. So these are the fadings. So if you want to see this ratio, it's a delay with respect to magnitude. In Asian model, both the line of sight and non-line of sight components are simulated between the transmitter and receiver. MATLAB provides this Rayleigh chain function to simulate the Rayleigh channel model. It shows the magnitude, band limited impulse response, magnitude and the delay. You can see here, it models more for the non-line of sight. This in Rayleigh model, only non-line of sight components are simulated between transmitter and receiver. It is assumed that there is no line of sight path exists between transmitter and receiver. So when the combination exists, you can use the Rayleigh ones. Okay. MATLAB provides a Rayleigh chan. Okay, this is Rayleigh chan in MATLAB. And for the Rayleigh, it is a Rayleigh chan. Okay, you can just get the MATLAB code. Uh, MATLAB, if you write, you will have the health function. You can see that. The phase is uniformly distributed. The power is exponentially distributed. MATLAB provides this function. The power is exponentially distributed here, and the phase is uniformly distributed and independent from the amplitude. It is one of the most used types of fading in wireless communications. So you remember the power is exponentially distributed in Rayleigh, and the phase is uniformly distributed and is independent from the amplitude. Whereas it was not the case for phase shift. Okay. So just give me a second. I will share week 12 assignment questions. So just now we saw Rayleigh fading is more applicable to non-line of sight, non-line of sight, and wireless channels, while the ratio is more applicable to line of sight. Whereas when the combination exists, you can use the ratio one, but when the combination doesn't exist or the only non-line of sight exists, then it can use only Rayleigh fading. The square of the Rayleigh distribution random variable has exponential distribution. Just now we saw that the magnitude of the Rayleigh distribution follows exponential distribution, whereas phase follows uniform distribution, and it is independent of the amplitude. Signal will distort. Okay, if the transmitted signal bandwidth is greater than the bandwidth of the radio channel, obviously because of the frequency selective fading. Because in the frequency selective fading, the frequency range only defines that their signal is constant and not good enough. And the variation of the signal strength as a function of distance in free space path loss model is 1 upon r square. I'll just show you what is path loss model. Its PT is PR is equals to PT. Usually the wireless communication channel is noisy, so we can't have the noise-free communication. Okay, so we often use the AWG model for the interpretation of the channel noise. The noise is assumed to get added to the signal and the receiver. We have a signal. We have a signal that carries both the data and the noise. It is important that the signal level in the receiver is reasonably above the noise load so that the detector can faithfully detect and record the signal. So basically, this is also happening in action. So this red color is a reflection. Okay. And this is transmitter receiver, and these are the diffractions. Reflection, refraction are those two different things. So apart from the noise, the losses in the atmosphere uh, can also distort the transmitted signal. Some of the common losses taken into consideration during the design of the wireless link. Budgets include atmospheric absorption loss, scattering loss, the reflection loss, diffraction loss, and the path loss. So this path loss actually refers to the attenuation or the attenuation or propagating electromagnetic signal encounters along its path from the transmitter receiver. So how mathematically it is defined? That's why I was just showing that. The path loss model is usually expressed as d path loss d is equals to 20 log 4 pi d by lambda, where d is the distance between transmitter and receiver, and lambda is the wavelength of the signal. As said earlier, the receive power level depends on the path loss. So the expression for the receive power at a distance d from the transmitter is expressed mathematically using phase transmission equation. So here you can see the phase transmission equation, and d is the distance between transmitter and receiver. Vt is the transmitted power. Gt is the gain of the transmitter antenna. Gr is the gain of the transmitter receive antenna. Lambda is the wavelength. So PT, GT, GR into lambda by 4 pi d square. This is PR. So these are the, you can see this TV scale. Give yourself a minute and you just can see that. Okay, so I hope you agree that it is 1 by r square. So here it will present the mean 0 and sigma square. So 1. Small scale fading arises due to multi-part delay spread. We know all this. These detailed solution you can see here because it actually arises to all the mentioned factors. Uh, the multi-part delay spread, the small scaling or fading is often a consequence of multi-part propagation where the multiple copies of the transmitted signal take different paths to reach the receiver. Because small cell means small distance is considered. The time delay between these multi-path components causes a multi-path delay spread, resulting in fading due to time dispersion. Doppler spread where when there is a relative motion between transmitter and receiver or the schedules. So all these things happen. So first is multipath delay spread, second is the Doppler spread, and the third is constructive and destructive interference of the multipath signals. So Doppler spread happens when there is a relative motion, specifically seen in the form of vehicular communication where vehicles are moving and they're transmitting also and they're receiving also. So that's why whenever we are in the area of one cell, when we go out of that other cell, the handover happens and suddenly the frequency drops down and signal drops down. Okay. So this droplet spread shift leads to the frequency spreading and is a contributing factor to a small scale fading. So, as a multipath signals arrive at the receiver, they can experience a constructive or the destructive interference, leading to rapid fluctuation in the signal amplitude. This interference is the primary cause of small-scale fading, resulting in fades and the enhancement in the signal strength. So, small-scale fading is characterized by the rapid variation in signal amplitude. That's primarily due to the complex interaction of the multi-path signals, Doppler phase effects, and the interference phenomena. So yes. Now what happened? Large scale fading. So large scale fading, for that only we saw this path loss model. Remember, the path loss model is basically for the large scale fading. So path loss model and shadowing. So all the effects are there. So both mention factors. Basically, the relationship between the signal strength and its distance is typically characterized by the inverse square law, where the signal power decreases with the square of the distance between the transmitter. There is a fundamental aspect of the large scale fading. Okay, shadowing for the large objects such as window, buildings, hills. Okay, that is more important. Now, the Rayleigh fading can be modeled as a radial component of the sum of the two uncorrelated Gaussian model. Why? Because I'll show you how the Rayleigh fading actually looks like. So basically, it's a this one. It is actually an exponential. Okay. So in that case, what is Gaussian also? It's also an exponential. So if you write in the form of two sum of two uncorrelated Gaussian random variables, it will look like a Rayleigh fading, like this. You just see once the applicability. Okay, so we covered all the questions of week 12. Let's see this also. I'll share some my screen to show you some more examples where we can see the actual practice of wireless communications. So using MATLAB is very important to visualize and analyze. We already saw these things last class. .pf chapter till chapter 3 I explained everything of communication laboratory using MATLAB. Digital modulation, we saw this. I was showing this particular thing. PPSD, QPSD, PSK 16 form. Scatter plots also we saw. And we did also some of the classes. So these were the commands. We just see these ones. here we are having these functions. I'll start pulse shaping and mass filter. We saw basically in MATLAB. So I'm just keeping this. Synchronization, eye diagram without and the left impairments. So this is a framing. Flat fading channel. You see this code, how can we have the cross correlation for the frame timing MF of the baseline eye diagram? If you have any doubt, let me know. Keep in the comment box. Basically, I have already taken an extra class 7th October. Only Parisha huge one, and unfortunately, that lecture couldn't be recorded. I will re-record that session and I will upload others to join. I hope this code is clear. So these are the works for you. You can take a screenshot of it. These are the some set of exercises for you. In the communication library, they will be as part of that. So what are the techniques being introduced in min, max, and the this var command? Make note of it. Chapter 6 is about frequency recovery. Uh, block diagram, fractionally sampled complex baseband model. I think this is not enough good required for you. But still see this modulo 2. So here, this is very important. Mobile app. See this. It's very good. Just a task from my side. How can you do this for a communication lab, a mobile lab? So for doing this, the physical layer designed for a communication systems is the use of constrained resources to maximize the system performance. The resources include bandwidth, power, system complexity, and the power and the cost. So performance is required, and here you can see this the carrier frequency 2000 samples per second, 110, and excess bandwidth is 0.5 per half width is 5 like this. It's very nice to see this. And the simple packet structure with a header of NTR symbols followed by a payload of NP symbols. So differential PSK modulation, I was telling you that we have different types of modulation techniques with specifically in the form of phase shift key. So see this ones. The frequency selective fading. This is what we were thinking about. So this is the eye diagram for the frequency selective fading. BPSK eye diagram for no ICI and intersymbol interference. This chapter is important in the sense that these are the linear equalizers for frequency selective fading channel, how the channel is utilized. block diagrams, linear equalizer. A square solution is simply simplified by writing a special form. Least square solution is basically to do the uh, minimizing the mean square error with respect to x input. And how can we do like this? This is how there are some list of experiments for you to do that. And these are some MATLAB functions. So I think this summary concludes here. Um, there is some channel capacity. I will take these things in the extra class. Stay tuned. And these are the parts of the wireless communication. Okay. So thank you so much for joining, Hanisha. You're the only student joined today. Save this as week 11 and 12. Okay. So yes, you can leave now. If you have any doubt, I'm waiting for 2, 3 minutes. If you have any doubt, you just let me know, Manisha.